Apologize, Zoom people. My mic was muted and the Zoom crashed before, and we restarted it. And yeah, I apologize. Fortunately, so Dustin saved the day just in time for the most important parts of the lecture. All the previous stuff was intended to be a quick review of the SQL constraints that hopefully saw in previous classes. And this is the part where it's actually becoming concrete and the important stuff for what you need to do. So the first concept is what we call a one-to-one relationship between two different pieces of data. So an example of a one-to-one relationship is that every film has exactly one title, and every title corresponds to exactly one film. And so the denormalized way of representing this type of relationship is just to have different columns in the same table. So we have a film table, and it has a title column because title is sort of like unique to a film somehow. The film has many other columns that have the same sort of relationship. The customer column, so every customer has exactly one name, and every name corresponds to exactly one customer. Every payment has either exactly 1 or 0 payment dates. So this is a nullable column. It has a payment date if the date is if the payment has actually happened, and it's null if it hasn't been paid yet. Quick aside is that you probably don't want to, in your databases, so in this database, they did a bad thing of storing first name and last name separately. In the US, everybody is basically required to have a first and a last name by the government, but other regions of the world, that's not true. You might have multiple last names, multiple first names, or like just one name, no family name. And so the sort of best practice is just to have a single field for the names. We can normalize these denormalized relations by, so again, extracting it out into two separate tables. The rental and the payment table are an example of doing this, that we could have, so in the payment table down here, like an amount and the payment date, the time that it happened. We could have had all of this just as a particular entry in the rental table up here, and it would essentially be the same exact meaning. But here, in order to make it unique to have exactly one payment for each rental, then we can do a rental ID unique references rental ID up here. And then if we joined payment and rental together on the rental ID, then we would have exactly one payment for each one of these rentals. Here, so again, the unique constraint right here enforces that rental ID, there's only going to be one rental ID anywhere in this payment table. So that means there'll only be one payment amount per any rental that happened. And this references right here guarantees that there is going to be exactly one rental ID in this table up here for each row down here. So that's why the unique makes it exactly one entry in the payment table. The references makes it so there'll be exactly one entry in the rental table up here. And so we get a one-to-one relationship this way. In the actual Padilla database, this unique constraint is not there. So this since the unique constraint is not there, you can have multiple payments for a single rental in the Padilla database. And so without the unique constraint, this would be a one-to-many relationship because you have one rental for many different payments. But with this unique constraint, it makes it a one-to-one. There's exactly one rental for each payment, exactly one payment for each rental. Any questions about this, how it's split off, or these one-to-one relationships? So good. A good question to be thinking to yourself is that we have, so there's this pattern that can come up in our data, one-to-one. We have two different ways of representing it. When should I use each of these different ways? And the answer is that you should basically always prefer the denormalized representation with this relationship, with this one-to-one relationship. It's yeah, strictly better. And I don't want to say all possible ways because there might be some weird edge case when it's not strictly better, but any way that I'm aware of. The normalized representation is, okay, I guess here's one way that it can be slightly better. You can force two columns to be inserted as either null or not null together. So like in this rental table, if I denormalized, here was the normalized representation. If I denormalized combining rental and payment into a single table, basically putting the payment date and the amount up here inside of rental, getting this. If I denormalize like this, now there's no way for me to have a constraint that both this one and this one are not null at the same time. If they're both null, then if they both, yeah, so by default, any column is nullable. There's no way in this denormalized representation for me to say that if you have an amount, you must have a payment date. If you have a payment date, you must have an amount. There's no way to enforce that, but you can enforce that, separate it out like this. Now both of these have a not null constraint attached to them. So anytime we have a payment that corresponds to a particular rental ID, if there's an amount, there must be a payment date, and vice versa. So I guess that is one advantage of the normalized representation is that you can do that. But if you don't need to do that, then you want the denormalized representation. Again, it's possible to use a check constraint that enforces, so the check constraint, so here's an example of the check constraint. You can have an arbitrary condition inside of the check constraint like this, and that condition must be true in order for a item to get inserted into the table. So here, this check constraint saying amount is null, payment date is null, or amount is not null and payment date is not null. This check constraint makes it so that we can have both of these two things be not null. Any questions about that? Okay, so in my opinion, Pagilla is a little bit excessively normalized. That rental payment table, I would combine those together into one. The film language table combinations, I would combine those together into one as well, because that language could just be a text column in film, doesn't have to be its own separate table. This would actually make it take up a lot less space. And similarly with the county, city, address, customers set of tables, I would probably combine those all into a single just address field inside the customer table. So this is the one-to-one relationship up here. And we said that, okay, depending on exactly how you do this, like with the unique constraint, it's one-to-one, but without the unique constraint, it's one-to-many, in the sense that you can have many of these payments for the rentals. And so that's what this next section is, one-to-many relationships. There's two different sort of normalized representations that we can use. The first one being arrays. And so here, this film special features, we've seen this before. Special features is an array of text inside the film table. This is one way to represent the fact that any film can have many different special features associated with it. Another way to represent this is you can create a new table with a foreign key. So here is our film table, and then we have the inventory table down here. And for every film, we can have multiple entries in the inventory. Like we have one Toy Story film, or there is only information about one Toy Story film inside of here, but we could have maybe 5 Toy Story DVDs in stock, and so we'd have 5 entries in the inventory. So again, this has no foreign, or it does have the foreign key, which enforces the one part, enforces this one right here. The foreign key enforces that one. It does not have the unique part over here, so we can have many of these film IDs inside the inventory, and so that's why it's a one-to-many. A lot of tables in the Pagilla database have this relationship. So film to inventory, customer to rental, store to staff. You can have one customer can rent many different movies. One store can have many different staff members. But one staff member is only going to work at one store, and one rental can only go to one particular customer. So the disadvantage of using arrays, using this more denormalized form in a single table up here, is that arrays are not a standard SQL feature. So in particular, they're not supported in MySQL or MS SQL, other systems that you might have used. Actually, off the top of my head, I don't know if they're in SQLite, but I don't think they are. The only other database I know of that they're supported in is Oracle, and you probably don't want to pay $1 million if you to use Oracle. And so for that reason, many people believe you should never use arrays. So far in this class, the only thing that we've seen that is not a standard SQL feature supported by everything is arrays. Another disadvantage of the arrays is that you can only have one column as the sort of many end. Over here, under special features, we only have one column here, the text type. We can't have both like a text and an integer associated together. Like we can down here, we have an integer and a timestamp associated together. We can do that in the normalized version. In the normalized version, we can have multiple types associated together. In the denormalized version, we can only have one type. So this film to special features table, so the film to inventory table here could not be denormalized into an array, but this text could be normalized out of an array into two separate tables. It's a little bit confusing to work with, as we've seen with arrays from the last assignments, that you should basically always use this unnest function. And if you're using indexing directly into an array, again, sometimes constant runtime, sometimes linear runtime, and that bites people in the butts. So if you want to see a specific example, here's an example. People thought they were using the O of 1 operation, but they were accidentally getting an O of n operation due to non-obvious things going on under the hood. So those are the disadvantages of the arrays. The advantages, main advantage of using the denormalized representation of using the array is that the disk usage is going to be significantly less. So here is the disk usage of the array type, that you have 24 bytes overhead, plus the length of the array times the number of bytes for the type. And all of that is going to go into a single column in the table. And so because it's in a single column, it can be toasted and compressed when it's particularly large, and so that'll make it take up a lot less space. In the normalized version, you have one row for each one of your entries, plus that 24 bytes of overhead, plus the byte for that particular type. So this number up here, always less than this number down here by itself, but then you also get the compression on using the arrays up here because it's in a single column and you can compress individual columns. Any questions about that? Okay. So personally, when I would use arrays versus not using arrays, if there's only one column in the many, again, or the joins are going to be rare, then, or updates and deletes are going to be rare. When we talk about the algorithms for implementing joins and updates and deletes, we'll see that those will probably be more efficient on the normalized versions. There's also a thing called Enums. that it's used in the Pagilla database. Postgres supports this only because MySQL supports it, and in order to make it easy to convert a MySQL database into Postgres, they support it, but it's strongly discouraged in your database design. So I'm not going to talk about it any further. Last important type of relationship, many-to-many. The most obvious way to think about it is like a bipartite graph. So if we have the film, an actor, every film can have many actors, every actor can be in many films, and there's this, and the way we represent that is with a film actor table that links those two film and actor tables together. Apologize, this is not showing up well on the screen up here, but this middle one in blue says film actor, on the left is film, on the right is actor. And there are no good denormalized representations for this. So this is one of the things that something like MongoDB just really can't represent well at all. The normalized representation is you have a connector table that represents the edges of the bipartite graph. So our film actor table in the Pagilla database is this connector table representing these edges right here. So film, here we go. So here's our film table, our actor table. We have the primary key right here for film ID, primary key for actor ID, and then both these two tables contain a lot of information about film and actors. This table right here, the film actor table, all it has is a film ID and an actor ID entries into these two tables right here. And then the primary key on two columns at once, indicating that we can't have more than one edge between a film ID and an actor ID. If there's an entry in this table, then we have an edge. If there's no entry in this table, then we don't have an edge. Yeah, this is sort of the canonical example, the easiest example in the Pagilla homework. There's a few other examples though. So like customer to film, multiple customers can rent one film and one customer can rent multiple films. And then here the inventory table acts as the connector table, or the payments table. Any of those intermediate tables between these two things can be seen as acting as the connector table. Any questions about the many-to-many relationship? Okay. So as general graph structures can be represented as well. No good, again, denormalized representations. Normalized representation is just a foreign key that references its own table. It's a common way to do it, or references a different table as long as there's a cycle in the foreign key references. No examples in the Pagilla database, but something like this, employee, where you have a manager which references itself like this, would create a hierarchy or a directed acyclic graph. All of these graph algorithms that you are familiar with from data structures, depth first search, breadth first search, Dijkstra's algorithm, Prim's algorithm, Kruskall's algorithm, so on. They can be implemented with optimal asymptotic efficiency using a recursive SQL query. We're not going to cover how to do this. There's links right here. If you want to see more about that. And finally, some references on general good database design if you're interested down here. Next time, we'll go over some examples with the Pagilla Homework 3. And in particular, there's some problems in there that take advantage specifically of the many-to-many relationships. And so we'll work through one of those. But that's it for today. If anybody has any questions, happy to stick around after class and answer them. But otherwise, that's it for class for today. One last quick thing. I think I forgot to announce this because of the Zoom crashing in the middle. But I'm not going to be able to have office hours today. I have to take my wife to the doctor, and so if you do have questions or want to see me about something, then now's the time to do that.